Welcome to Module 3.2.1. In this module, we will go over the nitrogen cycle. And so previously, we've discussed about the nutrient management. We got our 4R nutrient stewardship, right source, right rate, right place, right time. And we're going to kind of see that a little bit in action as to why those are important when we come to the transformations that occur in these cycles. And so nitrogen is one of the primary nutrients that we need. So when we apply the most fertilizer of, it's also one that has the most environmental impact, at least the most negative environmental impact. Nitrogen is actually the kind of primary gas that is in our atmosphere. Somewhere between 78 and about 80% of our atmosphere is actually nitrogen. Nitrogen is also important in amino acids, but most importantly, it's important in chlorophyll and photosynthesis. And so we can see here that, nitrogen is this central component of chlorophyll. Nitrogen is very mobile in the plant and in the soil as well. And so that's kind of why it's one of the most important ones that we focus on. It's very dynamic. These changes that we're going to go over here in this module, they happen all at the same time. There is no kind of separation or compartmentalization. We can have all of these transformations occurring at the same time. And so when we have a nitrogen deficiency, we'll see this deficiency actually happen in the older leaves first, because it's mobile. And so when I think about kind of how nitrogen comes into the plant, it will go up to the top. It will fill everything out, kind of like if you were to fill up a balloon full of water, that nitrogen is going to move to the leaves, the outer edges of the leaves, again, because it's that central molecule of chlorophyll. And so once it goes out there and kind of fills up, if there is ever a deficiency, the plant will send a signal that says, hey, I could use some nitrogen on leaf 3. And so the plant goes, okay, cool. Say you so-and-so send some nitrogen down to leaf 3. And so they get that from the older leaves. So here you can see this nitrogen deficiency happening at the top of that leaf, but not in the bottom. And so then that's kind of one of the easiest ways that we can see that. If you've ever applied nitrogen fertilizer, you know that when you apply it, you're going to get this big green flush. So that kind of gives you the indication about chlorophyll as well. One problem that we have if we apply too much nitrogen is that plant starts to grow a little faster than it's supposed to. And it becomes, it doesn't lignify. And so it becomes kind of flimsy. And if it can't hold itself up, it will fall over, and we call that lodging. Sometimes it can delay when a plant matures because there's still so much nitrogen going in that plant. It's still producing some other components that have not allowed it to reach that reproductive stage and then continue on to finally harvest. And then disease susceptibility, because when a plant is lush and green, there's a lot of energy in that nitrogen. And so diseases and insects as well are going to kind of look for the opportunity or that food source. So we have two plant available forms of nitrogen. We have ammonium, which is NH4 plus. And we have nitrate as NO3 negative. And so what's important to know about these two is that when you think about our soil colloids and we think about cation and anion exchange capacity, we would like to have our ammonium or our nitrogen actually be in the ammonium form because it has a positive charge and it will be held to the soil colloids. If it is negative, the overall net charge on soils is negative. And so negative and negative do not attract. And so this would have to be held to the anion exchange capacity, which is very small in most of our soils. And therefore, this is why we have a lot of that, a lot of nitrate leaching, because the soil colloids don't really hold on to that nitrate molecule. So for our soluble organic kind of one of the big things is, this is where I'm from. This is home for me. This is the Mississippi Delta. This is one of the largest agriculturally productive regions in the country. And a lot of kind of focuses on the fact that, you're dumping a lot of nitrogen into the Gulf of Mexico. But if you look here, and if we go back to watersheds, pretty much everything along this line all drains to the Mississippi. So everyone that's growing corn, all the concentrated animal feeding operations that are kind of in the Midwest, we're looking here at Nebraska and Kansas. We're looking up here at Minnesota, our Dakotas. Over here, we are looking into, this looks like it is going to be Illinois. We got Iowa in here. Some Ohio, Indiana, all of these are draining to kind of to the center of the at least to the eastern portion of the country, and then down out the bottom of the mouth of the Mississippi River. So it's really important to understand that there is a lot of nitrogen entering our water systems because we're so dependent upon it for our crop production. Okay, so moving into the nitrogen cycle, there are 9 fates of nitrogen. And remember, as I said before, that the majority of these are happening at the same time. So kind of having an understanding of what your soil environment is going to help you understand what transformations may or not be taking place. So the first one is fixation, and this is going to be like atmospheric fixation. There are legumes that have the ability, when inoculated with rhizobium, that they can actually fix the atmospheric nitrogen. And this crop that, the easiest one to think about is going to be soybean or peanuts. Next, it can undergo mineralization. Mineralization is the transformation of organic nitrogen or organic whatever to inorganic. So in order to be taken up by the plant, the nitrogen has to be it needs to be available as an inorganic form, and that is going to be ammonium and nitrate. We have nitrification. So as part of this mineralization, we have ammonification. It needs to be turned into ammonium. Ammonium can then be transformed into nitrate, and that process is called nitrification. The primary goal of applying fertilizer is for plant uptake. That's the most important reason why we're applying this. So this is actually kind of central to everything else. In order for the plant to take it up, it must be as ammonium or nitrate. If the plant is not taking the nitrogen up, then it's not ammonium or nitrate. And we'll see this in the nitrogen cycle as to why that's so important. Next, we have immobilization. And immobilization is the conversion of inorganic nitrogen to organic nitrogen. So mineralization is organic to inorganic. Immobilization is inorganic to organic. And kind of the way that I remember this is this I, meaning that it is as ammonium or nitrate, and will then be converted back into an organic form. Then it will need to undergo mineralization in order for the plant to be able to take that up. Next, we have nitrate leaching. And as I mentioned before, because nitrate is negative and because the overall net charge on soils is negative, we do not have that attraction, or it's not strongly held to the soil colloids, and therefore it can be easily leached. It's also very water soluble. So as it gets mixed into, or kind of gets dissolved into the water, as that water moves through our soil, it will take that nitrate with it. Then 2-to-1 clay fixation. And so this is a potential fate. It's not a major one, but if you can remember all the way back from Module 1 with those clay layers and our 2-to-1 clay layers, remember, they're the ones that expand. So our smectites and our vermiculites are the ones that expand. And remember the pockets? And we used to have, I mentioned that potassium can fit inside of one of those pockets and kind of lock that down. Well, we can have the same thing with ammonium, because ammonium and potassium are not only the same charge, but they're also the same size. And so we kind of have this isomorphic substitution where that ammonium can fit inside of that little void that is created by those atoms that make up the tetrahedral and the octahedral. And so once that clay expands, we get a rain, the clay expands, the ammonium moves into that clay structure, and as the water recedes and that clay structure starts to collapse again and kind of break down and shrink, it will trap that ammonium inside of that, and it will not be available to the plant until the next rain. Something moves up. We need to have some other cation to come in and kind of displace that. And then finally, two of the bigger ones that kind of cause us an issue, one from a production standpoint and then one from an environmental standpoint, are volatilization and denitrification. And so we'll go over these in the nitrogen cycle. This is where you'll need that printout that's in iLearn in that folder. And so this is going to be kind of where you fill this in again, and you kind of see where all of these different transformations happen, why they happen, and how they happen. Okay, so here is the nitrogen cycle with all of its, all the different transformations that can happen. There's a lot going on in here. Remember that each time we do something, nitrogen can take on any of these forms and undergo any of these transformations, sometimes all at the same time or very close to at the same time. So we'll go through these just a little bit one by one, kind of walk you through and show you a little bit about where these are. So we have N2 fixation, where these we have our legumes that have this symbiotic relationship with rhizobium. They can then fix those nodules that are on the bottom of that soybean plant or that legume, can fix atmospheric nitrogen and convert that from organic, or at least convert that into ammonium that is then plant available. So N2 is not plant available. Plants cannot do anything with N2, but the nodules that absorb some of that N2 gas can then convert that from N2 gas to ammonium. And so, behind photosynthesis, this is the second most important biochemical reaction. And as I just mentioned, that N2 gas is going to get converted into, at least at first, an organic form, and then it will be converted to an inorganic form. So the fixation of the nitrogen gas from the atmosphere will then be turned into some R with some organic structure that has some amino acid that will then be converted further into ammonium. And so this is where we go in for mineralization. So just be thinking about mineralization as we kind of go through this. So we have these two different bacteria, and each plant is a bacteria species specific plant. And so that bacteria invades that host plant root. It will create that nodule, and then that N2 is going to convert that, or the N2 is then converted into this organic form. So anytime you see an R and there's going to be some functional group or some amino group or some ketone or some organic chemistry, right? On the end of that R, what this means is there's a large carbonaceous molecule that has this amino acid attached to it, or at least the amino group. Not that you need to know a whole bunch about like the actual equation for converting this across, but there are these enzymes that end up catalyzing this into ammonia, which is NH3. And then that NH3 will then be converted into ammonium NH4+. So we go from, N2 gas to ammonia and water. And then, this can be, along with, some organic acids. The aminos ultimately turn into proteins. And so then that NH3 will then be converted into ammonium and can then be taken up by the plant. So once that nitrogen has become, it has been mineralized from inorganic to organic, it can undergo the rest of the processes within the nitrogen cycle. And so the goal of that is to be used by the host plant. It can be leaked out of the root and become available for some other surrounding plants or organisms. And then there will be those microorganisms inside of the soil that will kind of, these nitrogen exudates, those organisms will actually use that and immobilize it until they can convert some of that carbonaceous material, some of that organic matter into energy. And then it will then be mineralized back. So we're going back and forth between this mineralization and immobilization, back and forth, constantly. Okay, next we have mineralization. And that mineralization here is our amine group, our aminization. So we had nitrogen taken out of the atmosphere. It was then converted into this amine group. That amine group then undergoes, remember that we get to ammonia, and then finally to ammonium. So from organic to inorganic, mineralization. Not so much that you need to know anything about this aminization or the ammonification, just that these are they're like steps in the mineralization process. And so it must be first converted to a protein. Mouse. First, it must be converted to a protein. That protein is then converted to ammonia. We will get a hydrogen from somewhere, whether it be in the plant or likely in the soil, and that hydrogen will bind with this ammonia to form ammonium. And remember that this is a plant available form. Once that is now ammonium, it can then be taken up by the plant. It can be volatilized. It can undergo nitrification. It can be immobilized. It can be fixed in 2-to-1 clay layers. It can be held to the soil colloid. But most likely, it will be it will undergo nitrification. It will be oxidized into nitrate. So the next step in this process is nitrification. And not that you'll need to know this for, again, we're not doing the chemical equations, but we just kind of have an understanding that we have ammonium, and in order for this oxidation to happen, we need oxygen. So it's kind of important to understand what soil type that you have, because if you have a clay that is filled with the water is inside of that pore space and there's no oxygen, this reaction would not happen because there's no oxygen. Now, in a sandy soil, we would expect this reaction to happen much quicker because there is more oxygen in those pore spaces. We have macro pore spaces, and water drains very quickly through sandy soils. Another important thing that we need is this Nitrosomonas species. Okay, Nitrosomonas. And the way that I kind of remember this is there are 3 O's in Nitrosomonas, and we need 3 oxygens in order to complete this equation. So once it undergoes this process, it is converted to nitrite. Nitrite is toxic to plants, and so we need the help of Nitrobacter. The Nitrobacter species is going to very quickly convert that nitrite into nitrate. So Nitrosomonas converts ammonium to nitrite. Nitrobacter converts nitrite to nitrate. So some of the major requirements for nitrification are going to be, number one, we need to have ammonium because that is the base molecule that gets converted into nitrate. There needs to be oxygen, and so this is going to be in well-drained soils. It happens better in more alkaline soils, so somewhere between pH 6.5, 7, 7.5, 8. And that is because these Nitrobacter are sensitive, both of them, Nitrosomonas and the Nitrobacter, are sensitive to pH. And so when I talk about pH, and we didn't do that in this particular course because you didn't have the chemistry. So when we talk about pH, pH has an influence on kind of the movement or the ability of different microorganisms in order to perform these metabolic processes. This is typically going to happen when it's warm, so in the summertime. And then also we need to make sure that that our pH isn't too high, because the Nitrobacter are sensitive to, that's not the pH, it's sensitive to high ammonium concentrations. So we need to make sure that we have enough Nitrosomonas to run that process from ammonium to nitrite. And so once that has become nitrate, as I mentioned before several times, that we had this anion that is not held to the soil colloids very tightly. And it can either be taken up by the plant, because that's a plant available form. It can undergo immobilization because there's now a nitrogen source that microbes can use to break down high carbonaceous or high C-N ratio residues. But most importantly, and what we want to minimize, is this loss to leaching and runoff. And so because it's very water soluble, it can be, dissolved in that water and then carried off our site, off our field. It can be percolated through the soil into our groundwater. And many of us are aware that this leads to eutrophication and possibly groundwater contamination. And so what can happen is, in the 70s and the 80s, mothers were pregnant mothers were drinking the groundwater, and their babies came out, kind of had this blue color to it. They called this blue baby syndrome, or methemoglobinemia. And so what happens is that there was a high level of nitrite in the water. I'm going to back up to this slide. Let me back up here and see if this will make sense. Okay, so from here we have ammonium to nitrite, and then nitrite to nitrate. And so as this nitrate leached into the groundwater, it was then in an anaerobic environment. And so the microbes that were in the groundwater used one of these oxygens for energy. So we had high levels of nitrite in the water, and because nitrite wants to stabilize to nitrate, it needs another oxygen. And so when the mothers were drinking this water and the babies were also kind of absorbing that water with the nitrites in it, the nitrite was looking for an oxygen in the baby's blood and was pulling that oxygen out to make nitrate. And so what that was doing was causing this methemoglobinemia or blue baby syndrome, and these babies were kind of blue. Now, some of them may have passed on from that, but many of them could recover as long as they were given the oxygen, and that oxygen was resupplied back to their blood. And so the EPA, all up in arms, obviously, they're going to be up in arms about this, and they determined that the MCL for nitrate concentrations is 10 parts per million. All right, so now once it's nitrate, we undergo, it can be taken up by the soil, taken up by the plant root. So whether it's ammonium or nitrate, the whole goal is to have plant uptake. We need the plant to take this up, especially before it leaches through the system. Once it is ammonium or nitrate, it can be immobilized. And remember that immobilization is inorganic back to organic. So here we have an inorganic form of nitrogen that will then be converted back to an organic form. And the reason for this, if you remember back from our soil organic matter and our microbes, remember that ideal carbon to nitrogen ratio for microbes is 24:1. Well, if we start getting, somewhere between, above 30, we start having a net immobilization. So the microbes will then be looking for inorganic nitrogen in the soil in order to perform or get the energy to perform the decomposition of that organic matter. So that's why it's kind of important to understand that carbon to nitrogen ratio and how important it is, and what the microbes are or are not going to need in order to decompose the corn stalk, right? How much nitrogen will the microbes need in order to decompose that carbonaceous material? But if we get less than 20:1, so our legumes, right, our hairy vetch and our clovers, when we get less than 20:1, well, now we're starting to get a net mineralization. And mineralization being organic to inorganic. And plants can take up inorganic nitrogen. So we want to try and lower the carbon to nitrogen ratio of our soil so that we can have more plant uptake. I believe that we are missing, I think over here on number 6 is nitrate leaching. And so I've mentioned this several times. We know that it can leach to the soil because it is not held to the soil colloid. Here we have for our nutrient stewardship, how much fertilizer we're applying, when we apply it, and the source of that fertilizer. And so the next things that are going to kind of influence that are how much does the crop actually take up? How much is left in the soil how much nitrate is left in that soil, or even ammonium, that could potentially be leached. And then how much rainfall do you get, or how much irrigation do you use? Is the rainfall abundant and well distributed, such that we don't have a lot of movement through the soil, but we have enough water there that plants can take that up? And if nitrate is soluble in water, well, then the plant can take that nitrate up and it doesn't go into our waterways. Here is that 2:1 clay fixation where we have that expansion, and that ammonium can then move into the voids in between that octahedral and that tetrahedral layer. And then when that clay layer collapses, then we're going to have some fixation there. Again, as I mentioned, this is very minimal. All right, so we're going to wrap this up here going on with our two gaseous losses of nitrogen. And so the main one that we're worried about is going to be this volatilization, this ammonia volatilization, because when we apply urea-based fertilizers, urea has to undergo several transformations in order to become plant available. During those transformations, if the conditions are, I don't know if you want to call them right, or if the conditions are wrong, we can lose up to like 30% of our urea fertilizers that we applied. So if you apply 100 pounds and the conditions are, I guess let's just go ahead and say that the conditions are prime for this ammonia volatilization, then you could lose 30% of that. So you paid for 100, but your plants only got 70. And then once they only got that 70, there are going to be these other transformations that need to happen as well. Again, not need to worry about the chemical equations, but to have an understanding that when our soils become more alkaline, or that when we have these hydroxyls, a greater hydroxyl concentration, that we are going to want that one of these hydrogens will dissociate and form water, leaving us with ammonia and H2O. This ammonia is a gas, and it will be volatilized. And so there are a few things that are, kind of drive this reaction. Obviously, that if we have high pH or we have a large hydroxyl concentration, that we're going to get this, rapid movement from ammonium to ammonia. And so here is this table that just kind of gives you an idea of when you are at risk for these different losses. So high pH with soil, with a little bit of soil moisture, with no rainfall, and we did maybe a surface broadcast application. So remember that surface broadcast is one of the most economical, cheapest, quickest ways that we can apply fertilizer to our crops. And so if we call the buggy up and tell them to come out and broadcast fertilize in the wrong environmental conditions, and look at when this is, when the temperatures are above 70 degrees Fahrenheit, springtime, right? When we're, starting to move into May, when we're wanting to plant our crops, and we did a surface broadcast and we didn't get any rainfall, because typically when we go to apply fertilizer thinking that rainfall is coming, it doesn't. On a low CEC soil, which many of ours are, we're going to get volatilization. And so on the opposite, if we have a more acidic soil with a high pH, then we are not, maybe incorporate that, then we're not going to get as much volatilization. And so these are some of the best management practices that we can do in order to minimize some of these losses. All right, so next we have denitrification. So down here we underwent nitrification. We know that it's available for plant uptake. It's not held very tightly to the soil colloid, and the microbes are possibly going to use that for energy. Well, if it rains a lot and there's not enough oxygen in the soil, then not only are the microbes going to use this nitrate for the nitrogen, but they're also going to use the oxygen for energy. And so in a saturated soil, we would basically get a reduction. And so when we're talking about this in terms of changes and transformations, we're talking oxidations and reduction. Remember that oxidation, it loses, reduction, it gains. And so we are gaining hydrogens actually, or losing oxygens, whichever way you like to think about it. Ultimately, what we want to do is we want this we have nitrate down here, and we want that nitrate to undergo these processes. And so all of these reduction steps ultimately get us back to N2 gas. N2 gas can then be added back to the atmosphere. It can be fixed. One of the big problems with this is that if for some reason we have this large, we have a lot of rainfall, our soils are saturated for a long time, we get this, we start this process of denitrification, and then the water drains very quickly enough. By the time that water drains, if oxygen is introduced back into this system, then the reduction process stops. And if that reduction process stops right here, then instead of N2 gas being given off, we give off N2O, or dinitrous oxide. And that dinitrous oxide is 300 times more potent than carbon dioxide in terms of global warming. So this is kind of where they're pointing the finger at ag. They're going, well, wait a minute, you might not be producing a lot of this, but what you are doing is you're producing something that's very highly concentrated and difficult for the environment to kind of take back off. So here it is, this N2O gas is 300 times greater than the warming potential of carbon dioxide. So we need a few bacteria in order to continue this process. It is the Pseudomonas that is using this oxygen in order to get back to N2 gas. So low oxygen and alkaline pH, because that's kind of the environment that these microorganisms or these bacteria like. All right, so we need an alkaline pH because bacteria don't like the low pH. We need a pretty warm temperature. So we're used to seeing this. So we apply lime, we start growing our crop, we get a heavy rainfall, we've applied our fertilizer, we get a heavy rainfall, and we have these conversions from ammonium to nitrate. And eventually we will get a lot of rainfall that saturates our soil, and we will have this reduction process that ends up converting, or at least converts most of, or we would hope all of, that nitrate back to N2 gas. But if it doesn't, we could lose about 10 to 30 pounds of nitrogen, about a pound of nitrogen per acre per day. So we've got this thing where we apply this urea fertilizer. Some of that is volatilized through ammonia volatilization. The rest of it undergoes some of these processes between immobilization, possibly fixed to the clay, can undergo nitrification and be leached. And then ultimately what happens is we don't have enough plant uptake. So you apply 100 pounds of nitrogen, you apply it at the wrong time, you lose 30 pounds of that nitrogen to ammonia volatilization. So you've got 70 pounds out there left for all these other transformations. We're going to get some nitrate leaching, possibly. We're going to get some plant uptake, and it's possible that we get this denitrification. So you can see why this is so dynamic for all of these different transformations to happen inside of when we go to apply this fertilizer. And so that's why I kind of started with the nitrogen cycle, because it is the most dynamic. These changes sometimes can happen almost all at the same time or very close to one another. Like we could have volatilization and nitrification at the same time. We can have plant uptake and immobilization occurring, mineralization and nitrification both occurring at the same time. So it's very hard to predict the amount of nitrogen that you have in your soil. That's why it's important to take soil samples. That's why it's important to understand how much nitrogen is in your plant, how much you applied, how much is in the plant, and then kind of have an estimate as to what is left in the soil. The most important thing that we want to do is at least make sure that our plants have at least enough nitrogen in order to complete or at least meet our yield goals. With that, we also want to minimize the amount of nitrogen losses that we have to the environment. And the way that we do that is with that 4R nutrient management. And so we don't want to apply a lot of fertilizer early on in the year, well, because the plant's not going to take it up yet. And so if it's not being taken up by the plant, it's being lost to the environment ultimately. So understanding the nitrogen. All right, so that ends module 3.2.1. In the next module, we'll be discussing sulfur, and sulfur is kind of similar to nitrogen, not as dynamic, but still kind of has the same principles that we saw in the nitrogen cycle. All right, we'll see you in the next module.